Hello guys, welcome back to my video lecture series on the derivation of the Black-Scholes. This video marks the start of part 2 of my video lecture series, which is going to be the derivation portion. Now that we got all the prerequisites, such as the definitions of a financial derivative and how it depends on a financial asset, out of the way. Cool, so a very important idea that we discussed in the last video was the tug of war between a seller and a buyer. Regarding many financial instruments, but in this case we're going to specifically be talking about the premium or the price of an options contract. So we'll say that's represented as V. Now the seller wants to drive this price as high as possible, and the buyer wants to drive this price as low as possible, and the reason behind this was discussed because of the payoff ratios and how options play out in the real world, which can be seen through my previous 2 to 3 videos. Now the question we want to answer is as follows. What is the fair price to pay as a premium for any options contract? And this right here is the question that will be solved using the Black-Scholes. And why is this so important? Well, when we find a fair price, or a theoretical fair price, and we'll discuss that, why it's a theoretical fair price later on. But assuming we do find a fair price and a relatively good fair price for an options premium, then we can analyze an options chain for any given stock and find both undervalued and overvalued contracts. Now, typically when something is undervalued, we would want to buy or open a buy position on this contract. Now, obviously, there are many more option strategies that can be used, and I'll discuss all those strategies in another video lecture series later on. But as for what's discussed thus far, we've only talked about opening a buy position and opening a sell position and how those individual positions play out. But going back to the point, undervalued options we typically want to buy, and overvalued options we would typically want to open a sell position on these. Cool. Now we've been working with a high level of mathematics thus far, and we want to continue to do so. And the question becomes, how do we mathematically model our options price V? And it turns out this is quite a difficult question to answer, which requires a high level of mathematics, which will be discussed and derived in the coming videos. But in this specific video, I want to talk about what an option contract really depends on. So if we have V, V would be a function of some sort of parameters. And obviously these parameters will change the price of the option. Now, what might those parameters be? Now Now, just because of the definition of a financial derivative, we know for a fact that it will depend on our stock price, which we derived and discussed way earlier in part 1 of this video lecture series. Now, it may also depend on the strike price. It may also depend on factors such as volatility, maybe a risk-free rate, which we haven't talked about much, but we'll talk about that more in the coming videos, and maybe some more constant parameters. And obviously the biggest one is going to be time. Cool, so now that we have all of this, we want to create some kind of function to represent this. Now, obviously, just by looking at this, we can't just come up with a function, right? We have to use some kind of mathematical derivations to do so. But in this form, we can't do much. So what we do is put this in differential form, and we try to find dv. And when we use dv, when we differentiate our function for an option price, we don't want the constants. So the only thing that's really going to matter is going to be our stock price and our time. So essentially we're looking at dv as a function of s and t. And this is because factors like our strike price, volatility, risk-free rate, and maybe some more constants are going to be thought of as, like I said, constants. And when we differentiate constants, they will obviously be 0. So we can just disregard these at the moment. Now, in the real world, things like volatility and risk-free rate are not actually constants. But to incorporate, for example, volatility as a function of time or risk-free rate as a function of time, we would need much more complex models, such as Heston stochastic volatility model. I believe Hall-White model is another one that's used within the industry, and so on and so forth. But those are extensions of the Black-Scholes. And regarding the Black-Scholes, all of these constants are going to be considered, like I said, constant. The only thing that really matters is going to be our stock price and time. So now we have to essentially expand out dv, and because we can't just come up with a function for v, so obviously we're going to expand out dv mathematically and see what that gives us. And once we do that, we want to get rid of stochastic elements. This is because we don't want a fair price of an option in terms of a probability density function. We want a one true theoretical fair price for an option. And once we do all that, essentially we will get something called a PDE, or a partial differential equation, which can then be solved to get our function for our financial derivative price, or the premium price, as a function of s and t, and so on. Cool, so that's essentially what's going to be discussed throughout part 2 of this video lecture series. And the first part is going to be expanding out dv mathematically, which is why we're going to need a Taylor series. And this Taylor series will be discussed in the next video and how it'll be applied to derive the Black-Scholes.